Welcome. So in this video we are going to talk about another damage mechanism, that is going to be caustic stress corrosion cracking. Now we already know what is a stress corrosion cracking. A stress corrosion cracking is cracking due to stress and the process that we are running that equipment into. In most cases the stress can be applied stress, or either it can be a residual stress due to cold working or due to non-PWH material. So the description of damage, obviously this kind of damage will happen in caustic services. We have seen other damage mechanisms also, that is chloride stress corrosion cracking, amine stress corrosion cracking, sulfur stress corrosion cracking. So depending on what kind of process fluid that your equipment is handling, it can be subjected to either of these. So caustic stress corrosion cracking is characterized by surface initiated cracks that occur in piping and equipment exposed to caustic, that is some kind of a basic solution such as hydroxide solutions, at elevated temperatures, primarily adjacent to non-PWHT welds. It is a form of amine stress corrosion cracking. The temperature above which caustic stress corrosion cracking depends on the concentration of the caustic solution. There is a temperature beyond which your equipment will be very subjected to stress corrosion cracking due to caustic services, and temperature below that it will not be that detrimental. Affected materials: carbon steel, low alloy steels, 300 series SS are susceptible. Duplex stainless steel are also susceptible, but they have shown improved resistance compared to 300 series SS. Nickel based alloys are most resistant to this kind of stress corrosion cracking. Critical factors: susceptibility to stress corrosion cracking in caustic soda, caustic potash solution is a function of the caustic strength, metal temperature and stress levels. Increasing the caustic concentration and increasing the temperature increases the likelihood and the rate of cracking. Conditions likely to result in cracking have been established through plant experience and are presented in the figure 315-1. So we'll talk about that figure when we go there. So cracking can occur at low caustic levels if the concentrating mechanism is present. In such cases, caustic concentrations of 50 ppm to 100 ppm is sufficient to cause caustic cracking. Residual stresses from welding, that is, if you don't do post-weld heat treatment, then there will be residual stresses. This can also be a factor in caustic stress corrosion cracking. Or if you have done any kind of cold working to your equipment, that can also be a suspected area for caustic stress corrosion cracking. Thermal stress relief is effective in preventing caustic stress corrosion cracking. Crack propagation rates increase dramatically with temperature. Cracks can grow through the wall in a matter of hours during the temperature excursions, especially in concentrated caustics, or if the conditions promote caustic concentration. The concentration can occur as a result of alternating wet and dry conditions, localized hotspots, or high temperature steam out. Special care must be taken with the steam tracing or heat tracing design, as well as steam out of non-PWHT piping and equipment. Contaminants in the caustic solution, especially sulfides, regardless of their concentration, will increase the likelihood of stress corrosion cracking in non-PWHT carbon steel, including a low temperature area in figure 315.1. Affected equipments: caustic stress corrosion cracking can occur in non-stress relieved piping and equipments that handles caustic, including H2S and Meracepan, Mercaptan removal units, as well as equipment that uses caustic for neutralization in the sulfuric acid alkylation units and hydrofluoric alkylation unit. Caustic is sometimes injected into feed to crude towers for chloride control. Failure have occurred in improperly heat traced pipings or equipment, as well as heating coils and other heat transfer equipments. Caustic stress corrosion cracking can occur in equipment as a result of steam cleaning after being in caustic service. The traces of caustic can be concentrated in boiler feed water and can result in caustic stress corrosion cracking of boiler tubes that alternate between wet and dry condition due to overfiring. It can also occur in superheaters due to steam drum carryover. Appearance: now all types of stress corrosion cracking are generally similar. They look like a branching cracks. They are intergranular in most cases. and they generally starts from the process side and it can go beyond that. So caustic stress corrosion cracking typically propagates parallel to the weld in the adjacent base metal, that is the zone of highest welding residual stresses, but can also occur in the weld deposit or the heat affected zone and can be transversed to the weld. The pattern of cracking is observed on the steel surface is sometimes described to as spider web or small cracks that often initiate at or interconnect with the weld related flaws that serve as local stress risers. The crack can be confirmed through metallographic examination. Cracks are typically branched and predominantly intergranular. Cracking that occurs in as welded carbon steel typically appears as a network of very fine oxide filled cracks. Cracking in 300 series SS is most often transgranular, but it can be intergranular even in non-sensitized material. Prevention. So first prevention is don't increase the temperature. Second is going to be don't increase the concentration. Third is going to be generally do post-well heat treatment for your welding or whenever you have done cold working. So the cracking can be effectively prevented by means of stress relieving or post-well heat treatment. A heat treatment of 620 degrees Celsius minimum with a minimum holding time of 1 hour is considered as an effective stress relief heat treatment for carbon steel. The same requirement applies for repair welds and to internal and external attachment welds. In contaminated caustic solution, stress relief may be needed to prevent cracking of carbon steel even at low and otherwise safe temperatures. 300 series of stainless steel offer little advantage in resistance to cracking over carbon steel. Nickel based alloys are generally more resistant to this kind of cracking. Steam out of non-PWST carbon steel piping and equipment should be avoided. Where necessary, the equipment should be washed with water before steaming out, and use only a low pressure steam to be used for a short period of time to minimize the exposure. Inspection and monitoring. Now again, this is a crack. Crack can be identified by crack identifying mechanisms. That is, you can use UT, you can do PAUT, you can do shear wave UT, you can do magnetic particle testing, that is wet fluorescent magnetic particle testing for greater sensitivities, and you can also use penetrant examination. In some cases, acoustic emission can also be used. Sometimes RT can also be used, but it's not going to be that effective. Okay. So you can use wet fluorescent magnetic particle testing, ACFM, eddy current technique can be effective techniques to detect these surface breaking cracks. Proper surface preparation is necessary to ensure cracking is not masked by blending or smearing the metal into cracks. The method of surface preparation is dependent upon the specific technique. Angle beam UT, PAUT can be effective to detect and size cracks. PT-MT can also be effective. PT may not be effective in identifying tight cracks because cracks can be oxide filled. So in most cases we'll do MT, but if MT is not possible, we can do PT provided that whatever defect we want to identify is free of any contaminants. RT may not be effective. Acoustic emission testing can be good for identifying or locating cracks provided that the crack is growing in size. Okay, and it looks something like this. So this is the table that will tell you about the caustic service chart. So here you can see temperature, here you can see the concentration of caustic. So let's imagine if your temperature is 50 degrees, then your caustic concentration should approximately be 45. For carbon steel that is not PWST. If your temperature is 60 degree, the concentration should be 30% by weight. If your carbon steel is post-well heat treated, then at 80 degree Celsius, your concentration can be 40%. So as you do PWST, your concentration increases. And in nickel-based alloys, so generally the above area can be considered as the nickel-based alloy. Nickel-based alloys are generally more resistance, generally offer more resistance to these kinds of stress corrosion cracking, especially with caustics. And it looks something like this. So these cracks are stress corrosion cracking. So this crack is a stress corrosion cracking crack. Obviously it cannot be seen with a naked eye. You have to do some metallography, or you need to use a metallurgical microscope to identify this. Same things here, these kinds of cracks. This is also considered to be a crack that you can see. The same thing, mostly all stress corrosion cracking looks like this. So in most cases this is going to be similar, but the reason for these kinds of stress corrosion cracking can be different depending on what kind of processes you are working this equipment on. Same thing, you can see this crack. This is a stress corrosion cracking. The stress corrosion cracking in tubes, this is identified by penetrant testing. Again, spider web like appearance. Again, you can see this crack. All of these are metallurgical microscope images. If it's available, we can do this. If it's not, then we'll generally use magnetic particle testing or ultrasonic testing to identify these. So that was it for caustic stress corrosion cracking in this video. In the next video, we are going to talk about some other damage mechanisms in our damage mechanism series.